Hi, I'm Stephen Bartlett, and my project is looking at the influence of in-stream large wood on alluvial aquifer recharge at Indian Creek in Kittitas County, Washington. Indian Creek is a tributary to the North Fork Teanaway River. It is one of the locations of a large wood restoration project in the Teanaway River Basin. Specifically, what I'm looking at is, does wood placed in a stream channel have an immediate effect on groundwater recharge and thereby increasing late season discharge? Indian Creek provides an excellent opportunity for this project because the wood has only been in place for about 5 years. 2 years prior to the wood being placed, 4 groundwater monitoring wells were installed on the floodplain, and in 2018, 2 more wells were installed. So we have groundwater data from 2 years prior to the wood being in place and every year since. My methods involve stream model comparisons with and without channel obstructions at varying discharges, stratigraphic analysis of the floodplain and alluvial aquifer within the restoration area, and groundwater levels since 2014 from data logger and manual measurements. Model results showed a small increase in flow area and water on the floodplain. Increased water on the floodplain should increase the amount of water that percolates into the ground and thereby increasing the late season discharge into the stream. However, 4 months later, as you can see from these images, the stream channel is completely dried up and we see no late season discharge. Now we look at the stratigraphy within the aquifer to understand what the makeup of the sediment within the storage area is. Now if we look at a little background of the area, this geologic map put out by the Washington State Department of Natural Resources shows the Indian Creek area as glacial drift and outwash characterized by poorly defined layers of boulders, cobbles, pebbles, sand, and silt carried down by valleys by glaciers. And notice this area circled in red of glacial lake deposits characterized by well-defined layers of sand, silt, and clay. So if we go back to Indian Creek and take a look at the stream bed, we find that much of the stream flows across the top of a layer of clay, which is circled here in yellow on the image. So now, looking at one section of the stream bank, we see these well-defined layers of sand and silt and clay, much like we saw from the geologic map earlier of glacial lake deposits. Beneath the soil, there's a sandy silt layer with small pebbles. Beneath that layer is a nearly 1 meter thick, predominantly clay layer, followed by a sandy layer with large cobbles, followed by another thick section of clay. Looking at a 1.8 kilometer stretch of stream bank stratigraphy, starting at the North Fork Teanaway River and going up Indian Creek, we see very similar layers, including that thick clay unit right in the middle and another thick clay unit of gray clay at the bottom, which is not shown in 2-1 because I did not dig that deep on that bank. Looking at the stratigraphy within the floodplain near the monitoring wells and other locations, we continue to see beneath the soil the silt and clay, and beneath that dominant clay layer, which is shown in orange in most of the columns on the image except for 5-2 where that clay clay was all gray, and then that clay is followed by the sand, silt, and gravel layer. So why do I keep talking about all of this clay within the alluvial aquifer? Well, the presence of clay may be putting limitations on the storage potential of the groundwater at Indian Creek. Looking at this diagram, if you consider the light blue areas labeled unconfined aquifer and confined aquifer as sand, you can see that the water flows fairly freely through that. And if you look at the darker blue area as clay, which is the area of low hydraulic conductivity, you see that the water is nearly stagnant there. So although clay is highly porous, water just does not flow through it. The yellow marks on the diagram give an idea of how close to the surface the clay is at Indian Creek. And this image to the left shows stagnant water sitting on top of a clay silt area. This map shows the Indian Creek area. The groundwater monitoring wells are marked with blue wavy lines. The areas of stratigraphic analysis are marked by the starred yellow balloons. And take a look at the numbering of the wells, where 1, 2, and 5 are the lower wells, and 3, 4, and 6 are the upper wells. 4 is marked 5-3 on this map. The lower portion is a graph of the surface elevation of Indian Creek in blue, and the orange line shows the elevation of the base of the clay throughout the Indian Creek area. Notice how close it is to the surface in much of the profile. These are the manual measurements of the groundwater monitoring wells, shown in elevation in meters above sea level. The top 3 are the downstream wells, and the bottom 3 are the upstream wells. The earliest measurements were taken in October of 2018, and the most recent measurements were taken April 28th of 2021. No measurements were taken in the spring of 2020, so that data is missing, which is the reason for the large down curve on each of these graphs. Notice that MP1 and MP2 don't even reach the height of the water level in 2018, and MP1, 2, and 5 have experienced large drops in water level in just the 2 weeks from April 11th to April 28th. The upper wells have experienced less decrease in the later season, but have still not reached the same levels as in 2018. This is a not-to-scale cross-section of the Indian Creek floodplain, showing the stratigraphy columns and showing the groundwater levels on June 28, 2020, when well 1 was dry. As you can see, it is below the gray clay, showing that the water is likely always within the confined aquifer beneath all of the clay within the floodplain. Thank you to my 2 advisors, Lisa Ely and Carrie Gazis, in the Yakima Basin Integrated Plan and the Washington Department of Ecology.